few minutes was, okay, you looked at cyber physical systems and network control systems and all that, right? Okay. So the idea was, where is this heading? You know, where is this going? Okay. And what is the future? So I have only 4 or 5 slides here to just show you. And remember, I keep saying this to you many times. You need to know all this because most of you, let's say, many of you might go to an industry. And industry, you know, or you may be as a faculty, you want to educate your students. Maybe there is an opportunity to make changes to the curriculum, right? And so all that is necessary. You know, and so that's why we do all this. Okay? So 5.0. So I don't know whether anybody have heard what is 5.0 industry revolution. Have anybody heard 4.0? Huh? So what is 4.0? Huh? IoT and everything is integrated. So the network control system is a 4.0 industry revolution. So I'll show you some things in the video, but right now we are going one step ahead. What is in the future? 5.0. So 4.0 started like somewhere like 2007, and it may go until 2030, 2040. Okay? And then afterwards, you will start seeing that 5.0 will start coming up. Okay? So this is why maybe I won't live that long, but you may be living. And so you need to know what is going on, you know, in industry 5.0. Okay? So the 5.0 goals are improve the well-being of workers, that is the health, reduce environmental impact, sustainability, more make production more sustainable. Okay, that is the climate change, all that stuff. And help companies become more agile and productive. Agile, what is agile? Agile is very flexible. Very flexible and productive. Okay? So these are the goals of Industry 5.0. Alright? So that's what it means. So if you go back and look at it, so this picture would tell you everything. So if you look at the Industry 1.0, you know, it's mechanization, water power, steam power. That is Industry 1.0. Industry 2.0 is basically mass production, assembly line, electricity. That was done in early 19th century. Remember, early 19th century we have all cars, assembly line, you know what I mean? And then Industry 3.0. Industry 3.0 is mainly when you have computers and automation, and that happened in 1980s. Digital logic circuit chips have come out, right? Chips have come out. So those chips were there in 1980. That is Industry 3.0. Okay? Industry 4.0. Industry 4.0 is robots and everything communicating via wireless. So this is called cyber physical systems. So if you look at my intro to NCS, I started with Industry 4.0, you know. So that's what Industry 4.0. So whereas we are looking at Industry 5.0, mainly it is human and robot. So mass customization and cyber physical cognitive systems. Cognitive is human. Human, you know, cyber, you know, human machine systems. It's basically 5.0. Okay? So there's a lot of work going on in Industry 5.0. Okay? So I see some new faces. So you know tomorrow you have an exam, right? If you don't attend the exam, Professor mentioned, you won't get a certificate. So make sure you have to take the exam, okay? All right. So I don't know whether I can play this. I can play this. Maybe I can play. Let's see. The internet is connected. I don't know. No. It's not working. Let me see if I can. Yeah. Let me copy this. Huh? Copy? Okay. Go to another, yeah, open, yeah. Yeah, open that, yeah, copy, paste, yeah, let's see. Yeah. Oh, it's not coming in. No? Go down. No, I think it's not working. I don't know. It's not working. I don't know. 1 second. Let me copy that. Yeah. Copy that. Let's see if it. Copy. Yeah. No. It's not. Something is wrong. I think yeah, it's not showing up. So I'll pull up my laptop. Yeah, it's not working. So anyway, we have a issue. It doesn't work. So any case, so you see that cyber physical cognitive systems. So what it means is combining the capabilities of cognitive human. You see, there is a human, and cyber physical intelligence systems would help in tapping optimal benefits from the machines in terms of performance and purpose. So that's 5.0. So you are looking at even human in the loop. And also we have to have transparency. In today's rapidly connecting world, cheap business tactics of earning margins has no place for existence. Promoting transparency across the business and would customers help trusted employees and customers. So there is this transparency, so it has to be transparent. Okay? So 5.0, you see here, it's basically Industry 5.0 as essentially have human-centric, has to be sustainable, it's resilient. So what do you mean by resilient? Humans are very resilient. So what does it mean by resilient? What is the meaning of the word resilient? How many of you heard the word resilient? Everybody heard this? So what does it mean? Not robust. What is the meaning of resilient? So most humans are resilient. So let's say if some fever, we get a fever or we get hurt, then we basically don't give up. We take medicine and then we basically come back. Our body has resilience. What happens? Our body fights the virus. Remember that? Yeah, immunity. So it fights the virus. And pretty much so that it, normally we don't get it unless the virus replicates and all that stuff, right? That happened in COVID. So, but the body has the power to fight, some immunity. So resilience is a very important. So many times, many systems, you have to be resilient. Resilience comes from two aspects. One is due to faults. So if there is a fault in the system, then the system would fail. The question is, how do you avoid failure? The other case is, resilience is attacks. So if you have a network control system, people can create attacks like denial of service attacks, sensor attacks, actuator attacks. So the goal was to cause the system to be down, or to not to function. So I think these are the reasons why you have resilience. Okay, so you can see here the Industry 5.0. Okay, you see this Industry 5.0. You have enterprise agility, mass customization. This is what that is: cyber, physical, cognitive, green manufacturing, transparency in the business, people centric, and culture collaboration. So everything, so that is part of Industry 5.0. Okay. So what are the key features? Like we talked about it. So key features are human-centric. So it has to be human-centric. Human at the center of the production process. And you're creating value and well-being. Sustainable. Make productions more sustainable. So that means that, think about it. Let's say if the current process uses so much energy and so much waste, the 5.0 is supposed to have less energy and less waste. That is what it means by sustainability. Collaborative. Use advanced technologies to increase collaboration between humans and machines. So think about it, a robot carrying a table, okay, and you have a human there and you have a robot. So the human and the robot are trying to work together. Okay, so there are other technologies. So what are the technologies? You have robotics and machines operating autonomously. Remember, I already told you that, autonomous systems. Performing repetitive tasks so that humans can focus on creativity and experimentation. Okay? AI. Self-learning algorithms optimize production process. That's exactly what you guys are studying. So self-optimization, if you look at your entire MATLAB code, you are trying to optimize the processes, right? Batch reactor, two-link robot, pendulum. There are so many examples that you are trying to optimize it by using self-learning. Well, here self-learning could be online learning, So that's why it is a big deal, guys. It's a big deal, okay? Then you also have Internet of Things. You guys already talked about. Connected worker platforms enable real-time communication and collaboration between employees, machines, and systems. And last one is generative AI. So what is generative AI meaning? What does that mean? This is what Google, Microsoft, they're all doing this. What is generative AI? Right, so you have some data. Typically there's large quantities of data. I won't say some data. They really need a large quantities of data. And the goal was to create a large language model. Basically it's like a LLM, it's like a system that purely supervised learning. And then once it gets trained, then the goal was to create more data. And that data will be used to further train a system. That's basically what we call generative AI. Okay? So in this context, it's new technologies that enable people to think creatively and develop efficient and sustainable products. Okay? So that's basically. So here are the key features in Industry 5.0. Okay, there's more human side of it. In 4.0, there's no human. Okay? So, some of the examples of 5.0. Industrial Revolution. Collaborative robotics. So, unlike traditional robotics, here humans are going to work with robotics. Like I gave you a good example. One robot is on one side, the human is carrying it, and the robot will work together. Okay? Personalized medicine. This is something I mentioned to you. So personalized medicine means, remember, if somebody has diabetes. Now remember, the same dosage may not work for everybody. So we people have different weight, height, structure. So their goal was, if they can personalize the amount of dosage to individual person, that's the great. So that's what is personalized medicine, you know. Sustainable manufacturing. So integrating advanced technologies with a commitment to sustainability, manufacturing process could become more efficient and less wasteful. Like 3D printing. So 3D printing is supposed to reduce the waste because you're printing rather than you're not removing the material. Okay, subtractive printing is what they call the other one. And also to try to minimize the carbon footprint. Smart cities. Smart cities, you remember we had a smart cities where everything, you know, use IoT, AI, big data to improve urban infrastructure, public services, quality of life, focusing on enhancing the human experience in urban landscape. Okay. Last one is ethical AI. Now what is ethical AI? What is meant by ethics? So what is the meaning of ethics? Huh? Values. So what does it mean by values? So what are the values of India? Right. So in other words, the values are different from one region to the other. But there are some common values. One is cheating. So you don't want to create something that you cheat, right? You know, that's one of the things. That's called professionalism. The second is basically bias. So like, let's say you're developing a tool, a software tool, you really don't want to bias towards women, or you don't want to bias against men or against kids. You know what I mean? So the bias is a big deal, is very important. And those are ethics. There are a lot of ethics that come in there. So there are a lot of things that come under ethical stuff. As an engineer, ethics are highly important. So a lot of times safety. Let's say you make a product. You know the product has a weakness, but you don't tell people what is the weakness. That's not ethical. So let's say, you know, plastic, right? You know plastic. The plastic was offered, like this, plastic bottles was offered as an alternate for steel and other metals, right? But you know what is the problem with plastic? It's not biodegradable. What will happen if you drink like a hot thing in a plastic cup? What will happen? There will be particles from the thing will go into, and so what humans will get? Huh? Cancer. People can get cancer. That's the problem. Did anybody tell you? No. And you saw that happened. You remember lot of birds or even cows in India, for example, they were eating those plastic bags. And those plastic bags go into your stomach, and it causing all kinds of problems for the cow. Ultimately, the cow would die. So many people didn't tell. People who made these plastics never told the actual drawbacks of the technology. So India in that way very, very nice. You know why? Because we used to use what? Pots, mud pots, those are healthy, right? Or even some of the metals we used to use, copper, brass, olden times iron, those are seems to be healthier than plastic. So what I mean is, things are changing, right? We had those values, but you know what? We were copying from people. It's cheaper to make this plastic, and and if you remember, everywhere in train stations, the cups were plastic because they can reuse it. This is how they were selling it, right? You can reuse it, right? and it's not expensive. It's not expensive. So that's how everybody was selling it. But like she said, people realize that if you are using hot water or hot coffee or something, there could be some things from the plastic can go into the coffee. You can drink it, and if you consume it for a long period of time, it's not healthy. So that's a part of ethics, because the company that was doing that never revealed these are the dangers to the human. You see what I'm trying to say? So that's very important, ethical AI. The same thing with medication. Remember, even if you take a medication, every medication, English medication, has a side effect. So you don't want to take too much of anything, right? Side effect. So if you take something, your kidneys, it may affect the kidneys or heart, something. So like COVID, when a lot of people I heard, again, I'm not sure, I'm not a doctor, I don't have the proof, but I know I lost 2 of my friends, and you know what they said? Because they took the vaccine, and the vaccine caused the heart attacks. So there's no proof. I'm just saying, but it's the news, right? It's the news. So what I mean is, if people knew that the vaccine can cause some side effects, those have to be studied and understood. You see what I'm saying? So the doctors can prescribe accordingly. Even they don't know. And the companies may not tell you, right? You know what I mean? The companies may not tell you, otherwise they can sell their product. So ethics, very important. How does even ethics for an engineer? Like let's say that you build a car with a EV. And you are a battery, you are doing battery. But you need to tell, because lot of batteries can catch fire. Can catch fire. So as an engineer who's working with batteries and stuff, it's your job to protect the customer. You need to tell that, okay, don't do this, don't do this. You know what I mean? So we, as an engineer, we do a lot of things, and there could be problems like electricity. You don't want to touch it. You know what I mean? You can get a shock. There are so many things like that. So it's a job of the engineer to safeguard humanity. So that's an ethical part of it. So we have to tell them not just the strength, we also have to tell them the weaknesses as part of our, that's an ethical practice, okay? And a lot of times we don't do that. A lot of times no company would do that. Even some people said cell phones. Remember the cell phones? They say that don't use it too much close to the ear. People have said that it may cause cancer. So don't use a whole lot of cell phone, especially the antenna, because it has the radioactive waves, and it can cause ear problems. So I think it's very important to look at this, and when you're looking at this, it has to be safe. It has to be safe. So security. Remember I said sustainability as part of this. How does it affect control people? Okay. So here is the closed loop. This was done long time ago. So remember, you have a controller. You have a controller, and you have an actuator, and you have a system, and you are measuring as part of the feedback. And then it goes back, right? This is a typical closed loop block diagram, right? So you have faults. There could be faults, okay? The faults, whenever there is faults on any of them, you have a model. You have a model. This model is called digital twin. It's called digital twin. So this digital twin basically generates something, and then basically use that information to detect a fault. Then you configure the controller so the system could be safe. And I'll show you a video. I told him that I'll show once my laptop works, okay? So this is a very important thing when you have a fault. So resilience is against faults is also very important. Now why is that? Think about, you have a car, suddenly the brake doesn't work, then what will happen? The car cannot come to a stop. So you have to have some other way to bring the car to a stop without really crashing. So always it's very important to have a system with a resilience. Okay? So resilience doesn't mean redundancy. Remember that. Then let's say you have attacks. So in this case you have attacks on the controller, on the actuator, on the sensor. So the attacks, if the network control system, people can access the system through the IoT devices or through the network. So that's a problem. That is a problem. Okay? So security is a very important aspect for cyber physical systems or network control systems. So you have to take cyber states. You have to detect attacks. You have to identify the type of attack, and you have to mitigate the attack. You see? Any questions here? Very similar to fault detection and accommodation. Here you need to look at the cyber states. You detect an attack, you identify the attack, and you mitigate the attack. So cyber states are basically, you need to know the computer states. And so traffic is a cyber state. So if the traffic increases, a lot of times people create an attack by increasing the traffic. So you monitor the traffic in the network. If suddenly the traffic is going up, you know somebody is injecting something. So that's a cyber state. There are a lot of papers of mine published in this area. Quite a few papers. Okay, so we won't have time to look at it. Okay, so you use that information, then you detect the some attacks, and then you identify, and then you have to find a mitigation. So here is basically attack detection. So we use the same observer. One of the ways you can do attack detection is observer. Look at that. This was published in some conference, in also a paper in journal. So you have the attacker creates some data. So basically what they are doing is they change the delay and packet losses. So when they inject traffic, what will change? The delay and also packet losses too, it changes. And it's dangerous for control. It's dangerous for control because the control command can get dropped. You see what I'm saying? The control input can get dropped. And that's the problem. So you can use an observer. You can use an observer and you estimate the states. You see that? And then you predict the delay and packet losses. And from there, you basically decide whether there is an attack. So the idea was, this was published. And here is an idea. So we are detecting the network traffic. You are detecting the network traffic flow. And we use that to detect attack. And we estimate it. So you have an observer. You see that your traffic flow. You have an observer or a model. Then we use these two. We compare it. If it is above a certain threshold, we know somebody is injecting traffic. Then we build a detection residual. If this residual is greater than some value, if no, this, then you detect an attack. No, the attack not detected. Here attack is detected. Then you basically estimate. You estimate and you basically launch a defense. Okay? Any questions here? Somebody said he's working on denial of service attacks. I know in the first day of class somebody said he was doing something. I think he's not here today. Yeah. So that's That's something. This is called denial of service attack. So here is the proposed detection resilience. So here is the cyber layer. So cyber layer monitors the traffic and does the attack detection, and once you have that, then you need to adjust the controller gain of the physical system. So here this is the physical layer. So cyber physical system. Okay. So these two, between these two, what you have, guys? Between the cyber and the physical system, what do we have? What do we have? The network. That's how it is connected. The cyber is computer. The physical system is a robot, batch process, and they are connected by using that network. That is basically cyber physical system. So what you do, here also we use an observer. You guys have done that. We use an observer, we detect it, and then we basically decide whether there is an attack, and if there is a physical attack, then you estimate it, and then you accommodate the attack. You accommodate the attack. Okay? So you can adjust the gains. So there are several types of attacks. Jamming attack. The jamming attacker aims at creating traffic congestion by placing jammers that consistently inject data into the link. Look at that. You see? You see what I mean? Black hole attack. If the attacker manages to compromise one or more nodes, then part of the data will be discarded. So what happens is your control command will be discarded and the system will become unstable. Remember that. So that's a black hole attack. A minimum rate denial of service attack. The attacker periodically injects data into the network in order to minimize their exposure to detection mechanism. So here is the jamming attack, here is the black hole attack, and this is the minimum rate of denial of service. So number of injected packets or dropped packets or the total number of packets in the link. Okay. So this is the resilience. So look at that. So until now the system is stable. You see that? Until now the system is stable, running perfectly. Now there is an attack starts here. Okay, you see that how it deviates? You see that how it deviates, right? So error deviates, right? So what happens is here also the performance degrades. But then what you can do is you can adjust the gains, the feedback gains. You can adjust it, you can still keep it stable. But what will happen? As the attack propagates, so the error comes back. You see that the error comes back. But then what happens is the attack intensity keeps increasing. You see what I'm saying? The attack intensity keeps increasing. At about 20 seconds, you see that the attack keeps increasing, then the system will become unstable. You see that then the estimation goes out, and you see that how the error magnitude starts. So you only have a limited amount of time to adjust the gain to accommodate, and after that, so what do? You shut the system down. Okay? Any questions here? It is injected at t equal to 10. See here. Network attack is launched and increases at t equal to 20 seconds. As the amount of attack keep increasing, you can adjust the gains to keep it robust. That's called robustness. But that is not enough. That's why there's a difference between resilience and robustness. Robustness is you are using the bound and you are adjusting the gain. But you can only do so much. And the attack strength keep increasing, you cannot do anything. Otherwise it becomes unstable. Do you understand this? Okay. Any other questions here? Any other questions? So, you have to know if you have to survive in the industry. If you don't have these skills, it's very hard. Keep that in mind. Even though you are a control person, control techniques are changing significantly. So as a faculty member, you have to make changes in the curriculum. So when I visit IITs, first thing we meet after that is what sort of changes. Even when I was there in Anna University last year, they were asking, okay, can you help changing the curriculum? Yeah. Now, remember, did I learn all this when I was an undergraduate student? No. So I was interested in robotics, that's all I was. So that time the robotics was barely coming, so my master's was in robotics and computer science, okay? Then there is artificial intelligence that time, but those artificial is a real artificial, not natural. So you have to program everything. And we used to call that as if and then rules. They used to call rule-based systems called expert systems. I don't know how many of you heard of that. In early 90s, they used to call expert systems. Okay? So that means that a human has to program everything. There's no natural intelligence. So many of us, at that time I was a student, a PhD student. So we thought that's not good, because everything you got to program. So we said, let's change and let's see how we can make it more natural, just like human. That's why you have the neural networks. So 90s and stuff, all the neural networks came into picture. So just like I do, I also doing all this research, and I am also learning myself. Remember that. So the same thing should happen to you, like what happened to her. She's a faculty, but she's coming to this class learning what is out there so she can go back and help with her students. Remember, all three of them are faculty. So that's important. So if they are doing it, you should be able to do. Remember, they have a lot of stuff to do. They have to teach classes. They have their own families to take care of. Yeah. So I think those students who are here, you cannot stop learning. That's called lifelong learning. You continue to learn. You can't stop it. The minute you stop, what will happen? What will happen? If you stop learning, what will happen? What will happen? Huh? You will be stagnant, and that's it. After some time, you will be asked to leave. Yeah. You become stagnant. A lot of times people resist, but they can survive for a long time. Even in any campus, it doesn't matter. Any campus. So I think this is very important. Remember, I mentioned this in the day one. So my suggestion is take some machine learning courses. Those are very important, very important. That's why you have to have a MTech degree, at least a master's. Yeah. Okay. Any questions here on the resilience? Not quantizer. We don't do everything together because it's an industry. We take we take the network, packet losses, delays, and then we inject the attack. That's what we have done. See, it says under different network conditions. Yeah. These are in papers. Not in the book, but in papers. So this is why it becomes Industry 5.0. So we drive that. Yeah, we drive it. What is next step? You may not know, but I may know what's coming. Okay, any questions here? Any questions here? I think the tea is not here yet. Is tea here? Looks like. Okay, so we'll try to finish it quickly then. Okay? All right. Okay, so this is the resilience part. So there's a lot of work has been done on a network you can attack. I think I might have some video. Let's see if that video works. Okay. So this is a very recent US National Institute of industrial things, you know. So they came up with what they call trustworthy learning control systems. I'm positive none of you have heard of this. So what is trustworthy? Trustworthy includes reliability, safety, security, resiliency, transparency, explainability, and interpretability. All right? So this is very important. This part is extremely important. And that's what we are heading. All right? I think that's it. So any questions here, guys? Any questions? So that is the last lecture for the course. And after the break, we look at some videos. Okay? And then we are done. I did play that video that I won't play that video again, you know, but then we are done. Okay, any questions, guys? Any questions? So how many of you are PhD students here? So those PhD students have to really do a good job, because you will be the future. Remember that. You will be the future trying to guide India, whatever. So you need to be the one, trying to drive the technology. Remember that. Yeah. All right. Any questions, guys? Any questions now? So how many of you are prepared for the exam tomorrow? Huh? So my question is, did everybody ran all the MATLAB code for all the code that we provided? Did you guys run everything? Huh? Just ran it. Yeah. So and then you were able to compare and you saw the similar. Right. I think, but I understand. Remember, we all know, right? It's not going to happen in the 2 weeks. We all know. But at least we want to show you where the material is. You see what I'm saying? So that's all we are here for. It's not possible in the 2 weeks, because you see there are so many things that we have brought in, right? Now control is just one part. You have a machine learning part, right? Reinforcement learning. You have adaptive control. You have optimal control. You see how they all came together? So, and you have security, right? You see that we also brought some security. So it's a multidisciplinary. You cannot just expect that, okay, I'm just going to learn one thing and then I can do this. It's not going to happen. It's not going to happen. Some cyber security. Yeah, that's right. Because, you know, there are other attacks. We are not concerned, because we are only concerned because our system is real time. Now, people in computer science, they don't understand what poles, what zeros are, you know what I mean? So they don't know what happens in the real physical system. We understand better than them. So we need to know little knowledge about the cyber side. What sort of attacks can the network, have within the, and this causes problems to the physical system. You see? That's the most important. Yeah.
oder intelligenten Bausteinen, wie man es nennen mag, vergleichen wir das vielleicht mal so ein bisschen mit einer Lego-Steinwelt. Das heißt, wir haben standardisierte Bausteine, die wir hoffentlich relativ einfach zusammenstecken und zusammensetzen können. Jeder dieser Bausteine hat bestimmte Funktionalitäten und wir können sie zukünftig in einem solchen fabrikinternen Internet dann kombinieren.
A bottling plant for liquids, set up together with Siemens, is used to demonstrate the most important components of the intelligent factory of the future. Each bottle contains an RFID chip storing a precise description of how it has to be processed, which liquid, which lid, and which label. At each station, the bottle communicates directly with the machine, telling it how it has to be processed. At the end, a computer checks whether the bottle has actually been produced as desired. Factories with networked machines and products are already in existence today. In the future, however, these hitherto self-contained systems will be connected together in a comprehensive network. All devices, machines, and materials will be duly equipped with sensors and communications technology and connect to each other. These systems are known as cyber-physical systems. The highlight is that they communicate with each other and also control each other cooperatively.
Wenn Sie sich das Thema Industrie 4.0 angucken, dann basiert sie ja auf der Logik dieser Cyber-Physical Systems. Das heißt, Sie haben autokrate selbst arbeitende Systeme, die sich optimieren und sich gegenseitig austauschen und dadurch letzten Endes Produktion optimieren.
Ja, die Vision sieht so aus, dass wir ein Internet quasi hinunterziehen bis auf die unterste Ebene. Das heißt, jeder Sensor, jeder Aktor wäre damit quasi ein Teilnehmer eines Internet der Dinge. Jedes Gerät hat damit eine eigene IP-Adresse, ist damit adressierbar in diesem Netzwerk.
For the customers, this means tailor-made products at relatively affordable prices. For industry, it means highly flexible mass production that can be rapidly adapted to market changes, because in the future, product life cycles will be even shorter. Another reason why it's increasingly important to depict engineering across the entire life cycle. Maintenance, for instance, is planned in from the very start.
Wir haben ja bereits in den 90er Jahren mit Totally Integrated Automation entsprechend ein Setup gewählt, wo unsere Produkte und Systeme sehr gut miteinander kommunizieren können.
At Corporate Technology in Princeton, a cyber-physical control is being researched even today. The vision, the control, and all linked sensors are connected to the internet.
One potential scenario is enabling the PLC to react to utility pricing information in building automation. We can enhance PLCs to use simulation to calculate how much to pre-cool a building, with the ultimate goal of turning off the cooling system during peak times.
But that's just the beginning.
We've prototyped capabilities in a PLC to access big data in cyberspace in real time. And we've also enabled a network of PLCs to connect to a dynamic simulation of the entire physical process.
Siemens is shaping the future of industry. Connecting the real with the virtual world of production is making it possible to enter entirely new dimensions in quality, efficiency, and flexibility. The company is well prepared for Industry 4.0.
So that is the Industry 4.0, and you know, it's widely so that's in industry 4.0. Okay, so Industry 4.0, you see that video was taken in 2013. So it says 20 years, that's what I was saying, 2030 to 2040. But Industry 5.0 is already started. People are already trying to do some research and all that, right? I already mentioned to you. So this was very important video. I think good thing that it worked in here. Okay, so I think let me go and look at some videos that I said we'll try and play. So this video, I think this is for Bharat. This is mainly to accommodate faults. Remember resilience. So this was done for a helicopter. How do you detect faults and then prevent, early predict faults and prevent things to really bad happening, okay? So we took the data. I can show you the data, but we took the data and then we're using through MATLAB as a way of simulation. You see this. So let's say you have a helicopter, you have an actuator fault at 3 seconds. Okay, what would happen? The fault progresses, all right? So you don't know that. So that's what is happening. So if you can accommodate the fault, remember I was telling you, as part of the resilience, so fault accommodation kicks in at t equal to 6 seconds, then you can detect it, then you should be able to land safely without losing humans in there. So you can use this technology pretty much in every vehicle. You see? Okay. Any questions here, guys? Any questions here? So remember, we talked about the leader follower, right? Remember network control system. I was saying that I'll show you this video. So this one was implemented in 8085 processor. We have a follower. This was made in the lab, in my lab. It was built. And you see that wirelessly we are monitoring, and see there are two graphs. One is a desired trajectory, the other one is actual. The follower is following the leader, okay? And so it's going on a circle, the follower, and we are getting that information. So there is some communication wirelessly. And you can see that here is the desired, and then where it's kind of matching, the error. So that's the leader, and there's a follower. And you can see on the right, we are collecting the data in real time. We are showing, the leader makes a circle, the follower makes a circle with some distance. Now we are going to place a desired trajectory. Now we will place an obstacle. So it has 3 neural networks: observer, actor, critique. So you saw that it's supposed to avoid it, but then you see another robot, so it will wait. So we didn't program it, it will wait. Then it tries to change the trajectory a little bit, and then it goes. So if you remember, I said this paper was published in Transactions and Control System Technology sometime in 2013 or so. So 8085 processor, remember it's very old processor. You could do with the 3 neural networks, you can implement it. So whatever I'm teaching you, you can do it in hardware, in real time. Yeah. Huh? I'm not able to hear you. Operation what? Potential, yeah, that's what it's using some sort of a potential energy at the obstacle, and as you close up, the energy would go up, trying to give you a signal to deviate around the obstacle. That's right. So energy-based obstacle avoidance. Yeah. So the third one was a straight line trajectory. but the follower has to maintain a certain distance from the leader, and it has to have a bearing. So all this is measured. So you can see that how it comes, and so it's not using these lines. It's not using those lines. So you see that how it converged. So you see some error. Can somebody tell me why there is an error between the actual trajectory and the desired trajectory? Why there was an error? It's a wireless network. No. Okay, so remember, if you have a smooth surface, the wheels can slip. You're measuring your encoder measures the rotation of the wheel, and the wheels can slip based on, so that's due to the slippage. Okay, that's due to the slippage. So we do a lot of stuff. This is for the power application, monitoring. So you see that UMR modes, those are hardware built in my lab. So we do everything. It's connected to the power system to monitor. And is this wireless network control system? There we are trying to do that. So it's not my lab, this is a power lab. We try to do that. Yeah. I think I can pull that one up now. Yeah, I know. So we had that problem with the event triggered control, right? You are saying. Yeah. It's not here. So I have it in my stick. So this one, remember I said the drone with event triggered control. So you see, so we are flying indoor. So we are trying to play with the event triggered. How far can you stretch the sampling interval? Okay. So we were using a neural network controller, and I think one of them really doesn't get up. See? So what happens is, if you stretch it too long, it becomes unstable, it goes down. You cannot stretch the sampling interval. So this has got the event triggered control part, we are trying to stretch that. So in some cases, you could run it pretty good. So finally, we found a sampling interval or the Lyapunov condition. It flies pretty good. Okay, so I think we pretty much do. Let me see. Okay, I'll use that in a second. So this one I played this one. I don't know how to make it big, but this is indoor localization. So you want to localize it indoor environment. So this is detecting chemical agents through wireless routing protocols. So you see that it's hopping. There's no network. It's hopping, and then you can detect it. So you can do a hopping in a network. And we'll see, I'll play another video that's a little better than this one. Okay, let's see here. So this one is mainly the routing protocol between hops. It's not like a, and this is used in many industries. So if you see that the multi-hop routing and you have a shop floor where they manufacture things, so you have the different levels. So these are the hardware we built in early 2000, and the size of that is like a quarter. It has communication control. It's being used in monitoring bridges, planes. So if you want to test it, we are kind of doing some strain measurements. You see that route, that first hop. So from the first hop, it goes to outside. You just watch. So that was built. So there's a first hop, no line of sight. You see the LED blinking, it's receiving data. So you see this is the corridor. So it's going outside the room and so this will pick up. So it's displayed in the laptop. So this technology is very, very, it was picked up in 2000. It's called smart dust. I don't know whether how many of you heard. The name is given called smart dust. So you saw the dust particles, right? The dust particles, imagine the dust particle is it has got a little memory, it has got a processor, it has a communication, and it's a dust. You throw the dust particles, it organizes itself, and then it basically measures things and communicates. So there's a lot of technology used, and there's a lot of applications, both commercial and military. So I'm just checking what else. There are so many, but not of interest to you probably. That's why I'm not showing this. Okay, guys. So let's see here. So how do you test? You know, something is AI, right? So things like, you know, what is the real way to know whether something, remember I keep saying earlier in 90s we are programming. Now we don't program, we let the agent learn by itself. So what is the best way to test it? Is like if the computer can beat a human, or you know, do as good as a human. Okay, so there's a lot of work going on in here, and you guys have done Q learning, right? Now this is a deep Q network. I'll show you deep Q network. I don't know whether you guys have played any of these games, Breakout or Space Invaders. You played? Okay, so so then you are familiar. So you know, we were trying to look at it and see whether a computer can play and do better, can get a much better score. Okay, so you can see here, you see this bar moving left and right, and it can also go up and down. So that's your action. Okay, and then input is the image, just like our eyes, you're seeing that. So the input is the image, so you're feeding so many images. Okay, and the output is basically moving this bar left and right. Okay, so this work, some part of it is done with collaboration with IIT Kanpur. All right, so now if you look at this, so you know, this is before training. It does really bad job, because if the ball doesn't come back, it fails, right? So now this is a well-known, celebrated, what we call stochastic gradient descent. This is what all these Google and everybody uses, mostly stochastic gradient descent. You see that in the top there is this score. It takes a long time for the score to improve. Look at that. So you are not teaching that system what to do or how to do it. Okay, so unlucky run. So what we did, we developed our own method. Okay, and we tried it with using our own method. You see how quickly it learns. And look at the reward. So that's the beauty of the real time. That is the beauty. You see? So we are not teaching the system how to do it. We only tell them what to do. And the whole network is able to learn, understand, and make decisions, so that the goal is to maximize the reward. In this case, you're maximizing it because it's basically the score that you are trying to maximize. You see? So this is where it's going. Okay? So there are also other programs. We also have Space Invaders. So we have done, you know, quite a bit. You remember the hybrid stuff? The hybrid where we have combined some iterations, and that's the one. And there are so many videos. Those are all videos. I can sit here and play for 3-4 hours, you know, all of them. There are so many. We implemented so many hardware videos, mostly hardware, and this is basically the one, you know, you can run them, you know. Oops, These are different methods. They are completely different methods that how each of these methods work. See, the hybrid is the one that is a combination of iterations and once a sampling instant. So so this is how we evaluate something is really going well. So what is that, I don't have that stuff. It's actually a Q-learning, deep Q-learning. So you guys have studied the Q-learning. It's a deep network because we are using the images. And the images are being processed. So we provide so many images per second, just like you're watching, and then those images are being processed through the deep Q network, and they are making a decision in real time, left, right, whatever. So this is what I'm doing right now. There's a lot of work going on right now in my lab. Yeah. So there's a lot of, this is a closed loop problem. So remember I said you don't teach the system, but let the system figure it out. Use the agent figure it out rather than teaching it. Okay? So I don't have all the slides, but I think there are so many different versions on this. Yeah. No, this is another one. So somebody told us, can these modes work under the water? So we dipped it under the water. This is electronics. So we dipped it under the water and we are kind of detecting stuff under the water. So the issue is some of these electronics, you're afraid, right? You put the phone down inside the water, sometimes it may not work, but no problem. So one of the projects we had was, can the electronics work under the water? And that's what that demo was. This was my campus. I thought I'd show you. So if anybody interested for PhD, it's a chance. Okay, so, and these are hardware. These are all hardware-oriented demonstrations, not just MATLAB simulation. I can't tell you the reasons what we are doing there, but it's being used in a number of applications that. So you can see in the beginning, that goes under the water. You see there's a water thing, and you'll see that in the tub, we dipped that whole thing inside the tub. You can see that. You try it, it won't work for you guys. Yeah. Okay. So let's see, what else? There are other ones, I don't know what this is. Yeah, localization. I think the professor is not here today. He was asking all the localization stuff. Yeah, I won't show that. So anyway, guys, there are a lot more stuff I can show. Any questions here? Any questions? I don't know what else specifically you want to. Yeah, I don't know. So can you ask him to cut it? That's enough. Yeah, you can record. Stop recording it. Okay, just chop it off. A little bit? Okay, we can, but anyway, I'll say this because I don't know whether what situation I am in. Because I'm counting days, right? You know? So, what I want to say first, there's a thanks that goes to him and also to the professor who were there who was trying to help set it up, and NIT Roorkela, the help that they have provided, right? We'll do that in the valedictory. But what I'm saying is, but also there's a lot of effort that, and also the GIAN program, which is the Ministry of Education, that provided the funding to invite people like me to come from other countries to come and basically provide that knowledge, because as I said, it's very important for you to see that wherein you saw that video that I showed you, that's a German video that was taken 2013, that's Siemens. And you see that where the technology is going, otherwise you're out. You're out. So there are a lot of things that I was saying that, so we have to thank the GIAN program for helping an NIT, the EE department to hosting us, and as I said, Professor Bera and other professor, because I told him I have a back problem, and so they helped me, and then they know I can't carry the laptop, so I got this stick, they provided the laptop, we were doing all that stuff, and they used to bring me from the guest house, it's not that far. So they were trying to bring all that stuff, we have had all these arrangements that were made, yeah, and it was not a simple thing to do. So you have to thank him as part of the NIT. If you're an NIT student, you see that how much pains the faculty go through to bring all these things to the students. Yeah. So the only thing the faculty will ask you is what? What do the faculty would ask you to do? Huh? To study, to attend these and take care of these opportunities, right? Take these opportunities, whenever it's offered, you just be present, attend, and that's all. It's free for most of you, right? Remember that. So that's what is needed. Keep that in mind. Okay? And as I said, this is what is going actually, the reinforcement learning, machine learning. Even this professor today I met from Jadavpur in the guest house, he got excited, immediately said, can you give a talk he said in Jadavpur they're having a conference, 2 conferences in December. It's now conducted by IIT Indore. He said, can you give a talk? It's a big deal, machine learning. Yeah, he didn't know this. He's from production department. So it's a big deal. Yeah. Keep this in mind. So thank those 2 that are here today. You never forget. These are not easy, guys. It's not that they can go home at 5 o'clock, 5:30. Yeah. And you become like this, then you appreciate how much time they invest in you. Okay, the hope is that you guys become successful and you become in the forefront for India. You see what I'm saying? I think that is important. All right? Thank you, guys. So I think today at 2 o'clock we are going to meet for the last tutorial. Anything you want to add for the tutorial and for the exam? Yeah, there's a book on event triggering. I thought I'll show you. Okay, maybe I'll show you the book. Okay, because there is a little thing in there. I was thinking of showing that. But there are a lot of MATLAB code, and there are also a lot of probably hardware. So, but I'll show you the book that came out. Let me see if I can. You can hear me? Yeah. So this book is just came out, but I think he's going to give you a little code. So this is the book that was published last year, June. Oops. Okay, and you see those 2 are my students. Vignesh is in South Carolina, he's a faculty member in computer science, and Avimanyu Sahu is a faculty member in University of Alabama, Huntsville. So he's also a faculty. So this book came out, and this, if you buy this book, you have like a bunch of MATLAB code. You see that the ones, and you can actually see very basic stuff that we show. And the chapter 1, if you look at chapter 1, that's all you need to see. And you know, I didn't have time today, but if you go into the chapter 1, it has a comparison, very nice comparison of this is 6. There's nothing here. I think so this book has, if you look at it, there are so many chapters. So background and introduction to event triggered control. So if you look at this book, it has some math preliminaries that, like you heard, out is stability, impulse dynamic systems, vector norms, okay, and also it compares some matrices. There are a lot of stuff in there. So then stability, different forms of stability, okay, and then it talks about event trigger control systems, and it has different type of continuous time event triggered. It kind of gives you a table how to do this, and you know, there will be some comparisons, some simulations. So this is model based. Remember, I showed you the model base for linear system, and here is the flow chart. Adaptive estimator I did a little bit, and here is the zero order hold event triggered control system. And then, you know, there is a simulation that we compare. So we compare performance of zero order hold, fixed model base. You see that these spikes are the sampled instance, and then the one that we did adaptive. You see that how many sampled instance you have? Very few sampled instance that you need, but you are able to maintain the same performance by using that. So this would reduce. So we are comparing the data traffic on the network. So this book came out in 2024, last year. So if you want to order a copy to your library, I think that's another way to do it, and they will give you the MATLAB code, just like what you got, okay? But I think he has some examples that he has that he's also looking at it, Professor Rivera, okay? Anything else you want to? Yeah, 2 p.m. I guess we are going to meet.
Okay, so welcome to the assignment number 4, the tutorial 4 also. So I gave 2 problem. Problem 1 is related to basically the chapter, one second, the chapter of the book by professor, that is chapter 8. Okay, so this distributed joint optimal network scheduling and controller design for wireless network control system, where you have corresponding, I guess, the slide also you have followed. This is the corresponding slide to that. In the first part, there is no event triggering stuff. Okay, so the first part, basically this layer, cross layer communication and the issues related to that, it has been discussed. So theory I am not going to discuss, already it has been discussed by sir. Now you have to correlate this thing with the system, what it is provided. But if you see the book, you will find that for this particular application, same way it goes. And what I want to mean that you just focus on the algorithms, what it has been discussed, 8.1, 8.2, and that how this utility function, because all these you will find in the programming, it has been calculated. Then how the utility function is maximized, then this BI, how it has been calculated in the programming, that you will see. But one thing I want to mention you that if you see in this book you have that batch reactor problem. But the programming what I have provided, that is not the batch reactor problem, that is a system which is different from this example. So first you can study that example and see that how the things are going, and later on you can do the programming for the batch reactor also. So mainly you have to, because this thing maybe as a control engineer you are not much familiar, because here you will find that the communication related terminologies are also there. So you need to understand those terminologies and the values what it is given. Okay. So much thing I will not, I'm not telling here, just you will see that how the programming is working. You can run it and you can see that and programming in that particular folder what I have sent, it is, you will find that 2 folders I sent, one is 8 and 9. So you will see the chapter, and good thing is that this programming for that advanced MATLAB is not required, because this laptop I have 2018B and that one having 2024, but the programming is running with 2018 also. So there is no issue, you can run it. No advanced version is required. Like here you see, you have to open the chapter 9.1. Okay. And if you see the system is as it is given in the book, in the assignment sheet, that is AC, you see AC matrix and BC matrix is given. Then with the DARE, the gains are calculated. This P matrix, K matrix is calculated. But before that you have to do the discretization. Okay. One second. This is your 8. I have to open the 8 one. Yes. So this is the programming I am talking about. One second. You come to the second problem. I am doing the wrong thing. You come to the second problem. Second problem is related to, actually, sorry, the second problem is related to the chapter 8. There is a mistake I did. The problem 2. This is batch reactor problem. Correct. The second problem, it has been changed, means the event triggering part. So this problem 2 you now first focus. The problem 2 is related to the chapter 8, problem related to chapter 8. And you open that chapter 8 underscore 1.m, that particular file you open, and there you will find that we are dealing with a batch reactor system where AC BC matrix is defined. Then this AD and BD, the discrete version of that continuous time plant is calculated. Then the gain has been calculated, okay, and subsequently you will find that here you will, if you read the problem statement, then you can do it. You see that wireless network system, all 10 pairs to be used for this problem. And just to run it, and you see that the things what it is discussed in the class, that you can visualize it or not. Then I will come to the event triggering part also. So this is the network latency. You can remember sir has discussed about this, that how your, whenever there is a transmission, how it is coming down, okay, so, and how the delays are managed, that sir has discussed. And this is the final plot. You can say that all the regulator errors are coming to 0, okay. So that is required to be done for the problem which is discussed in the chapter. Yeah. Which one? That yeah, means the programming. Okay. Yes. Oh, here 8 and so that need to be open. Utility comparison, yes. Okay. It is to be run. No, to run this, I think the new version is required, because it having DARE command, which is not running here. What is the problem you tell? Yes. Of dimension of? Okay. Okay. Why that so? Okay, I will see that. When I will go there, I will see that. So main program is running in 2018, but other that, if you want to do the comparison with utility and the cost function also, you have seen that cost function. Okay, after completion of this, I will see that what are the problems you are facing. That if I am able to address, definitely I will do. So then you can go for that the theory which is discussed in chapter 9, that is event sample distributed network control system. Okay, so here first of all you should know that what is event sample. I guess now little bit sir, after sir's discussion, that it is clear that what do you mean by the event sample distribution. Okay. So for this little bit I can help you, because I am also working this particular area, event triggered control. So bit I can help you with some small example, then you can slowly you can extend that idea for this particular example also. So just to show you one example is simulated, very simple system I have taken. I am starting with continuous plant, then I will switch to the discrete one also. Okay, so you see that continuous plant I have taken, that is x dot equal to ut. It is a scalar plant. Okay, so now my objective is to stabilize this plant, to find out a u such that I can stabilize this plant. Okay, so the simplest control will be ut equal to minus xt. I can choose the state feedback, that is minus xt. So what is the solution of this system? For any initial condition it will converge, because it will be e to the power minus t into x0. Okay, which can be shown with a simple Lyapunov function also, that if you take a Lyapunov function half x square, then if you take the derivative of it, ultimately you can show it v dot will be equal to minus 2v, which is the condition of exponential stability. Okay. So now when you will, so this is the continuous implementation, but you see if you want to implement it in discrete or digital domain, definitely you have to take sample. How you will implement this control law in digital computer? Means discretized means na continuous plant can be also controlled by computer. Then at that time what you have to do, not necessary that plan has to be discretized. That is one way to do that, but continuous plant. But now you have the measurement x. Okay, now you can sample it. And now how you will sample? Generally in digital control, what you have studied, what is the sampling technique you have studied? So it is called periodic sampling. Means you will decide that based on certain issues, you will decide that okay, I will sample my signal, that is xt, suppose 0.1 second you have fixed. So then once you will fix that the sampling is 0.1 second, your subsequent samplings are known to you, because next sampling will be when 0.1, 0.2, like that, you know. That is the periodic sampling. Means you know once your sampling is fixed, you know what is the consecutive sampling instances are. Okay. So now in contrast to that, what we can do, we can do the event based sampling. We will not do the sampling at periodic interval. Instead of that, the decision when to sample and when not to sample, it will be decided by a triggering law. Triggering law will tell you, you now sample. Okay, and other time it is not going to sample. And in that way, what will happen? What is the advantage if you go for the event based sampling? Sir has already mentioned. What is the advantage of event based sampling compared to the time triggered or periodic sampling? Less computation, as well as the less number of samples you are going to pass through the network. Okay, so then essentially the congestion will be lesser, bandwidth requirement will be lesser. That is the motivation to use the event triggered sampling. Okay, so now in case of event triggered sampling, you do not know really that what could be the next sampling instant, like your periodic sampling. Periodic sampling, if you fix that 1 second interval you will take, then 1 second, 2 second, 3 second you will take. But here really you don't know that when you are going to take the next sampling. Okay, So then how we will decide that when to sample, when not to sample? How we will decide? What is the way? By some condition. What condition? But how we will derive that condition? Okay, so for that, you see what we are doing for the event-based strategy. What we are doing, we are telling that this sir has also shown this measurement error ET we are defining, which is the difference between xt minus x of tk. Okay, xt is what? The current state of the system minus the last measured state. That is the error we are defining. Okay, now you see, now the control law, instead of x of t, we are writing ut equal to minus x of tk. Okay, then what is your x dot will be? In a closed loop system, if you apply this control, then it will be your system was what? System was x dot equal to minus ut, and then you have taken that control will be minus of x of tk. So then you are writing x dot t equal to minus of x of tk. So which can be also written xt minus of xt I can write. So now you see x dot t, which is a closed loop system, which is equal to minus xt plus error. Now you see this error term is not there, then it is very easy to say about stability. For all initial condition it will be stable, but now you have a error. Why that error has come? Because you are not doing the sampling at regular interval of time. Due to that, one error is going to be generated, and which is going to evolve with respect to time. Now, how can you determine the stability of the system, or how can you guarantee that the system will be stable? Now for that, again you will take the help of Lyapunov, and you will see that what condition you can impose on error such that you can guarantee the stability of the closed loop system. So then same Lyapunov function we have taken v equal to half x square, and then we are finding that v dot x is coming minus x square plus x of e. You see this additional term is there. If it is not there, then it is very easy to decide about the stability, because minus x square, it is positive definite, so it will be negative definite definitely. Okay, so now this can be written with the help of mod, because it is a scalar case, that which can be written less than equal to minus x square plus mod of xt plus mod of et. And now we are saying that et mod of et is less than k into xt. K is a design parameter. Okay, and now if we will substitute that condition, now you see that v dot x can be said negative definite only when if you say that 1 minus k square is greater than 0. And this condition, norm of or mod of et less than k of xt, can be used as a stabilizing condition, or it is the triggering condition. Means whenever the error is going to cross this threshold, it is a state dependent, basically the law, and whenever the error is going to cross this limit, then you do the sampling and the error will come to 0. Okay, then you allow the error to grow. Then error is growing over the time, and whenever you are crossing the threshold, then again you take the new measurement and then you come. So like that, the event, then what will happen? You can delay the sampling. Whenever is required, you are doing the sampling. Whenever means what? Whenever you are finding that it is violating the stability condition, then only you are triggering. Otherwise, you are sending the old measurement. Old measurement, yes. So then only you can send the new data and you can update the control. Okay, something like that. And you see it has been plotted for this particular small example. You can also try this one, that you see that dotted one is a continuous one, and for two values of k we have plotted 0.8 and 0.2. Okay, the control law is this, and this figure is D figure is very interesting, because you see for red one this is a cumulative triggering, means how many number of triggering you are doing to stabilize the system. In case of, you are finding that for the red curve, it is almost 30 number of triggering are there within the 5-second time of interval. But in case of the blue one, you are finding it is around 11 number of triggerings are required. So it means that, or also you see, we are not compromising the performance also. Almost similar performance between red and green, and also if you compare with the continuous time, it is almost similar. So, but what is the advantage? Advantage, you are finding that the number of samples are lesser. Okay. So same idea can be extended for the discrete time also, and that now I'm showing you. Now you can correlate what is that particular one. You see, sir has shown this particular slide for the zero order hold scheme. Okay, so here you see we have taken a discrete time system, and now we have a sensor, and we are defining the error, that is xk minus xi. So this is the measurement error we are talking about. Okay, and now we have to find out a stabilizing condition, which will be my triggering law, and if it is violates, then it is going to be triggered. So you see, subsequently we found out that condition. You will find that that condition is this. You see, this is the condition, and it is in terms of error only. So so this is a stabilizing condition you have to, and how you can ask that how it can be found out. The same, using the stability condition only. So all event triggering cases you will find that like that, and you will find that sir was talking about another called model based. Okay, so you can do that kind of triggering from this paper also. This is the paper in sir's book also it is cited, that is model based event triggered control with time varying network delays, by this particular paper in CDC, you see in 2011 paper. So here they showed that if you have a system x dot equal to ax plus bu, and you have a model of the system, then you are comparing between the ideal model and the system, and whenever you are not happy with the performance, then you trigger. So you have to define a condition that okay, my error must grow that much of level. Okay, so now that's why if we come to the, so here similar way, you see the way I have discussed, I have shown that they are finding the system in terms of that error. Okay, and once this error has found out, and then they are trying to find out a condition on error which is the stabilizing condition or the event triggering condition, and if it is violated, then you will do the triggering. And if you come to the MATLAB programming, the MATLAB programming is we will take the system given by them only. This is the system we are talking about, A and B matrix. This is given in your assignment. Okay, so now for this system, the three strategies you can implement. Actually, the programming what I have sent, that is 9 folder 9. In that you will find that three strategies are there. You have to extract that one and you can compare. Okay, so I have actually done that extraction. You will do that one like the beginning what we did. You will split for time triggering is there. Then you have that particular ZOH based triggering. Then you have model based triggering. Then you have adaptive model based triggering. So these are the three strategies. In fact, four strategies you can see and you can compare. Like here, the first programming, if you see, it is for the time trigger. Here you see, here we have taken a sampling time 0.1, then we have a continuous time system, okay, and then we have the discrete time system, and then we are defining the Q and R, the performance indices, and then from DRE command we are calculating what should be the gain and what is the P matrix, and this is the initial condition we are defining, and then this is the loop where we are calculating the state as well as the control. Okay, here no event triggering is there. Simply u equal to minus k into x of tk we are applying. No event triggering, nothing. Simple control that u equal to minus. So now if you run it, then you can see that the system is giving the response like this. This is the control, and this is the two states are converging. Okay. Now next you can go with other programming, that is the event triggered one. You see now event triggering one I am opening. Same system. Now we will apply the event triggering scheme, which is a Z08 scheme I am talking about. Okay. So now the same system we have taken, and then we are discretizing the system. Then the Q and R, everything has been defined, but now you will find that little bit changes are there. Where the change? I am telling. You see, now here we are defining that stabilizing condition. This is the, you will in this, yes, that slide you will find that one stabilizing condition is there, that we are evaluating. Okay. And based on that we are applying the control. You will find that here there is a strategy to apply the control. What it is telling, this is the way you will apply control. uk equal to k into xk when event is initiated, and uk equal to k into xy when event is not initiated. Okay. And what is the meaning of this event is initiated and event is not initiated? That depends on the error. Error, when it is 0, then event is initiated because x of tk minus x of tk, so that is 0. But here you see when x of k minus x of I, then event is not, means error exists. A finite amount of error exists, so then event is not initiated. You will check this condition, and then based on that you will apply the control to the system. And then you will find that if you run that particular, I will close this to program, and now based on this, if you rest of the things are only to store and computation, that error, control, state, these are the things are there, you can do that one. And if you run it, now you see now new features. Now first thing that are you finding much difference between the stabilization performance once you have seen before with time triggered? No. You see almost similar performance you are getting. And this is the control effort. This is the control effort. Okay. And most interesting thing is that a new thing here, you will be able to see that evolution of that norm of error. Okay. What is the meaning of this? You see, you are allowing the error to grow, and this is a threshold. Okay, whenever it is going to touch that threshold, then error is coming 0. Why? Because at that time you are updating control. How you are updating? By sending the new information, current information of the state to the system. So then when you are applying the control with the new information, definitely the error is going to be 0. So in this way, eventually you are finding that error is tending to 0 and your system is stabilized and you are getting the control. But here another thing is not plotted. You can try that one, that the inter-event execution time, that is the difference between ti minus 1 minus ti, this difference. Then you can see that it is not in a periodic manner, it is more sparser than periodic. Means with less number of samples you can stabilize the system. So this is the whole theory behind it, and lot of paper, as sir said, you will find a lot of research till now. Many system, you will find that situations people are using, because all are now talking about CPS, network control system, IoT, where these issues will be there, that the transmission of packets and transmission of information through a common channel, okay, which will be constant by bandwidth, which will be constant by packet loss, everything. Okay, so if you want to minimize the adverse effect of network control system, then definitely one of the way you can solve with the event trigger. So that's why this particular chapter is dedicated that event sample distributed network control system. So I hope that rest of the thing you can do, because main part that is event triggering, and then the theory which we have learned in this particular course, it is clubbed with this, and then you can test the same thing, that effect of that here the optimal control that you can have with this. Okay. And if you able to get the 24 book written by Sir and what is the name, Abhimanyu. So then you can see at the beginning these things, 3 strategies are discussed. That is with ZOH based, model based, and adaptive model. At least if you learn these 3 things, your many things will be clear. You can go for any other application with event triggering case also. Okay. So you can see the main this is a chapter 9.1. Okay. So you can basically you can extract the you see, I was not knowing that this is there. How I come to know? By looking only. I'm not getting time to I'm not getting time to see the programming. Yesterday night only I saw this program and I found that okay, this way the things are, and all the, when you are reading something, most interesting thing is that everything you should look. You see, it is written at the beginning, example from Gracia and Antacyclis. Okay, so then I saw that okay, let me see this paper first. Then I downloaded that paper night only. What time I send you the programming? It is around 12 o'clock. So I was actually lying down and looking the programming. So that is the thing you have to also do. That you have to see the things, you have to play with the things, then only the things will come to your mind. Otherwise, no one can push you or feed you. Okay. So then I saw this paper and I saw that okay, this is the theory, it is written here. I am working in this field, I know little bit of this, true, but really I have not read this paper before, because I am not using model based triggering. So then I go through that and I understood okay, this is the philosophy, and it is written very nicely in Sir's book, very compact way with the steps. And if you see the pattern of Sir's book, what pattern, have you seen what is the pattern? Can you see? Can you tell Sir's book, how the book is written? And also with Sir's supervisor, F.L. Lewis, any book if you see, the series of book written by Sir's supervisor and Sir's, what is the similarity you are finding? You will find that after discussing every algorithm, he will give a table. In table, you will find that what is your system, what is the control law, what is the other necessary things. So you will find that 4 or 5 steps it will be written, that if you use for programming, it will be great help. It is summarized. No need to really look into the details of that. Details definitely you have to see, but programming I am telling, you can do that one. So this is the way you can play with that. Also you will see that cost function comparison, fairness comparison, all these comparisons are there. So you can do that one. But to understand this little bit of communication stuff also you should know, because we do not have that much of strong background of communication, but at least if you see with the fundamental background, you can understand that one. So I hope that that's all from my side. Now little bit I will roam around to see what the problem you are telling to me. and go back and you see only. You see, this is the comparison for three algorithms, that is proposed distributed scheduling, then embedded round and robin, and greedy scheduling. These are the three algorithms they are basically, and fairness comparison also you can do. I think this will okay. So then you play with the code. So I will stop here, and then in between you need any discussion, we will do that one. Okay. So I'm stopping here.